Bismillahirrahmanirrahim. Assalamu alaikum, students. Last time we were discussing the Carnot engine. We will continue this topic today. So I write here continued. We said last time that in 1824, Sadi Carnot, who was a French engineer, described an ideal reversible engine working in a simple cycle between two heat reservoirs and found the theoretical limit for the efficiency of an engine in terms of the temperatures of the heat reservoirs. Such an ideal engine is now called a Carnot engine, and its cycle is called Carnot cycle. We said Carnot's results are given in a simple theorem called Carnot theorem. Last time we stated that. I repeat here that statement. We said no engine working between two given heat reservoirs can be more efficient than a reversible engine working between those reservoirs. And after that, we discussed the corollary to Carnot's theorem that all reversible engines working between the same two reservoirs have the same efficiency. Then we stated the same theorem and corollary in terms of refrigerators. So theorem says no refrigerator working between two given heat reservoirs can have a greater coefficient of performance than a reversible refrigerator working between those reservoirs. The corollary was all reversible refrigerators working between the same two reservoirs have the same coefficient of performance. Now today we are going to discuss Carnot cycle, right? Carnot cycle. Now the Carnot cycle, that is the cycle performed by the working substance of the Carnot engine. It has 4 steps. There's 4 steps. First step is isothermal expansion, right? Second step is, let me use different color. Second step is adiabatic expansion. Then third step is isothermal compression. And fourth step is adiabatic compression, right? There are 2 isothermal processes involved in the cycle and 2 adiabatic processes involved in the cycle. And there are 2 compressions and 2 expansions. First, the gas is isothermally expanded, then it is adiabatically expanded, then it is isothermally compressed, and then it is adiabatically compressed in order to complete the cycle. You know, isothermal processes mean the temperature of the system during the process remains constant. That means during these two isothermal processes, the temperature of the gas, which is a working substance, temperature of the gas remains constant, right? This is one thing. Then what is another thing? You know how we perform an isothermal process. You must remember the idea of heat reservoir, right? When we perform some isothermal process, we put our system in thermal contact with a heat reservoir, right? Whose temperature is same as that of the system. That means during these two isothermal processes, temperature of the gas stays constant and the system or gas is in thermal contact with heat reservoir, right? Right? So in these two isothermal processes, the system or gas is in thermal contact with heat reservoir. Then another thing I need to highlight here, let me use this color. In these adiabatic processes, first law says dq is equal du plus dw. Heat put into the system is used by the system in increasing its internal energy partly and in doing work on the surroundings. Now, during these adiabatic processes, heat put into the system is zero, right? And our system is adiabatically isolated. Our system or gas is adiabatically isolated from its surroundings, right? You need to remember this. That means we have enclosed our system using adiabatic wall. Let me show this cycle on PV diagram. So the cycle is like this. Let me use now another color. Let this be 0.1. Let this be 0.2. Let this be 0.3. Let this point be 4. So So gas goes this way first, then this way, then this way, and this way. So this is isothermal expansion step, right? This is adiabatic expansion, right? This color. This is isothermal compression, and this is, I think black is better. This is adiabatic compression, right? So first isothermal expansion, then adiabatic expansion, then isothermal compression, then adiabatic compression. Now during this first step, I said during isothermal expansion, my system is in thermal contact with heat reservoir. Now here I specify in isothermal expansion, my system is, if this is my system, it is in thermal contact with hot reservoir. It is hot reservoir. It will have temperature, so hot reservoir at temperature TH. So from point 1 to point 2, my system, my gas undergoes first an isothermal expansion. So throughout this, the temperature of the system is TH, right? Throughout this, temperature is TH, same as the temperature of the hot reservoir. Since it is an isotherm, system is in thermal contact with hot reservoir. So system expands against the surroundings, so it does work. And that work is area under this portion of the curve. This work, you know that. We show it part wise. This is my first step. So the area under the curve will be work, right? And you know, if it is an ideal gas, if my system is an ideal gas, then during isothermal expansion, its internal energy will not change because the change in internal energy is zero. We have already discussed the isothermal expansion of an ideal gas. Its internal energy will stay constant. So work done by the gas against the surroundings will be equal to the heat put into the system, into the gas from the heat reservoir. So during this expansion, my gas, ideal gas, takes amount of heat which we last time represented by QH. It absorbs QH amount of heat from the hot reservoir, and that amount of heat is same as this area because that will be equal to work done by the gas, right? So at point 2, then what we do, we remove this system from the hot reservoir, and this is my system. Then we put adiabatic wall around it. Adiabatic wall around. So we ensure now no heat enters or leaves the system. Then we allow the gas to expand from 2 to 3. So gas does work. That work is equal to this small area, this small area. So let me use the colors for you. First I said in isothermal expansion, gas does this amount of work, right? And that work is equal to heat put into the system, which is absorbed by the system from the hot reservoir. Then at point 2, we replace this hot reservoir, we enclose our system in the adiabatic wall, allow it to expand against the surroundings. It does work, and that work is this area, right? Now, during this adiabatic expansion, if you already know, I'm just reminding you, dq is equal to du plus dw. dq is 0, so dw is minus du. That means work done by the gas is at the cost of its internal energy. So internal energy of the gas decreases, so temperature of the gas decreases, because U is function of temperature only. You already know that during adiabatic expansion of an ideal gas, its temperature reduces. So from 2 to 3, the gas cools down. It does work, that is this much area. That work is at the cost of its internal energy, so its internal energy decreases. That leads to decrease in temperature. So from 2 to 3, temperature of the gas decrease. Now at point 3, temperature becomes equal to the temperature of the cold reservoir. Now we have cold reservoir at temperature Tc. So we, in third step, we take our system, replace adiabatic wall. We remove adiabatic wall, not replace, we remove adiabatic wall. Now bring the system in thermal contact. This is my system. This was my system here, right? Bring the system in thermal contact with cold reservoir at point 3. Now the system is in thermal equilibrium with cold reservoir, which has temperature Tc. And what we do, we compress the gas. That means surroundings do work on the system, or gas does negative work on the surroundings. So gas is compressed from 3 to 4 isothermally. So during this curve, during this isotherm, temperature of the gas is Tc, same as the temperature of the cold reservoir, because it is in thermal contact with cold reservoir, right? So when we compress the gas isothermally, what will happen, right? We are doing work on the system. Now here also temperature stays constant, internal energy stays constant. So heat will be rejected by the gas. So heat rejection will take place. System will lose heat to the cold reservoir, which we already denoted by QC. Modulus indicates the amount. So it will reject heat to the cold reservoir, right? And the amount of heat rejected will be equal to the work done on the gas, and that will be this area, right? Got it? So from 3 to 4, work is being done on the gas. The temperature of the gas is equal to temperature of the cold reservoir Tc. Heat rejection takes place. It loses heat to the cold reservoir. Now at 4, what we do? We take our system. We use We take our system, right? Again, this is my system, and remove this cold reservoir. And what we do, we again enclose our system in adiabatic wall. This is my system, right? So at 4, my system is enclosed in adiabatic wall. Then we again compress it adiabatically, right? So no heat enters or leaves the system. We adiabatically compress it until it reaches 0.1. So this much work, this much work is done on the system, right? The area under the curve, and the temperature of the gas increases. In adiabatic expansion, temperature decreases, and in adiabatic compression, temperature of the gas increases until the temperature becomes the temperature of the hot reservoir, right? So at 0.1, cycle gets completed. Then the process is repeated. That means then again we have to remove this adiabatic wall, bring our system in thermal contact with hot reservoir, then it will expand, right? Reach 0.2. Then you have to remove the this thermal contact, bring our system, enclose our system in adiabatic wall, allow it to expand adiabatically, right? It will do work, its temperature will decrease, it will become equal to the temperature of the cold reservoir, then cycle goes on, right? So the net work done by the system, we've already discussed in PV work and PV diagram topic. Net work done by the system is this area enclosed in the loop, this. So this area is what? Net work done by the gas in the cycle. It's net work done by the gas. Let me bring my pen back. It's my pen. Okay. It's net work done by the gas in the cycle. I repeat, first gas is allowed to expand isothermally. During this process, the system is in thermal equilibrium with hot reservoir. It absorbs QH amount of heat from the hot reservoir. Temperature is constant, that is TH. Then from 2 to 3, it is adiabatically expanded, right? During this process, temperature decreases. It does work against the surroundings. Then it attains the temperature of the cold reservoir. Then it is bring in contact with the cold reservoir. During that compression, heat rejection takes place. Then again, it is adiabatically compressed in order to increase its temperature. Work is done on the system. So during whole process, whole cycle, the area enclosed within the loop is equal to net work done by the gas in the cycle, right? So during isothermal expansion, heat absorption takes place by the gas. During isothermal compression, heat rejection takes place. Gas rejects heat to the cold reservoir, right? During adiabatic expansion, temperature decreases. During adiabatic compression, temperature increases, right? So this completes our Carnot cycle. I hope you have understood it. Now I will give you some homework. An engine works between reservoirs at 400 Kelvin and 300 Kelvin, extracting 100 joule from the hot reservoir during each cycle. What is the greatest efficiency possible for this engine, and how much work can it perform during each cycle? I repeat the question. An engine works between reservoirs at 400 Kelvin and 300 Kelvin, extracting 100 joule from the hot reservoir during each cycle. What is the greatest efficiency possible for this engine, and how much work can it perform during each cycle? Then I will give you question 2. My question 2 says, what is the greatest possible coefficient of performance of a refrigerator working between reservoirs at 400 Kelvin and 300 Kelvin. I repeat the question. What is the greatest possible coefficient of performance of a refrigerator working between reservoirs at 400 and 300 Kelvin? Another question. Question third. My question third is, an ideal gas initially at at 20 degrees Celsius and 200 kilopascal as a volume of 4 liter. It undergoes a quasi-static isothermal expansion, isothermal expansion until its pressure is reduced to 100 kilopascal. Find part A. The work done by the gas. The work done by the gas and part B. The heat added to the gas during the expansion. During the expansion. I repeat the question. An ideal gas initially at 20 degrees Celsius and 200 kilopascal has a volume of 4 liter. It undergoes a quasi-static isothermal expansion until its pressure is reduced to 100 kilopascal. Find the work done by the gas and the heat added to the gas during the expansion. That's all for today. Do your homework. Don't waste time. Thank you. God bless you. Assalamu alaikum.